All right, let's get started here. How's everybody doing? It's week 10, Wednesday. This is our last lecture, and then on Friday you'll have your test, and then we're done, right, with this class, which is it's a tiny bit sad. It's a tiny bit sad for me, but maybe not for you. But okay. So the final questions are up online. You guys have seen that, so I'm hoping just it feels okay. All right. Okay. Let me find my notes here. And we'll continue on in the article Gibbs Sampling for the Uninitiated, and we'll talk about kind of this the model that we've set up for kind of document classification, right? So Gibbs sampling for document classification. And, because of the hierarchical nature of our model, we are able to factor our joint probability over everything into a series of conditional probabilities, which makes it suitable, right? So for Gibbs sampling. So we've got the probability of kind of our entire corpus, and the vector of labels, the value of pi, the vector theta 0, which is the word probabilities of documents labeled 0, and theta 1, which is the word probabilities for documents labeled 1. And then we've got the hyperparameters gamma pi 1, gamma pi 0, and gamma theta being a vector. Okay, and we factor this into, we've got the probability of pi given gamma pi 1 and gamma pi 0. This being a beta distribution. And then we've got the labels drawn from a Bernoulli distribution with parameter pi. We've got the word probability vector theta 0 drawn from a Dirichlet distribution with parameter gamma theta. The word probability vector theta 1 drawn from the Dirichlet distribution with gamma theta. And after we've drawn the word probability vectors, we can draw the corpus of documents in labeled 0, given our word probability vector theta 0 and the document labels, and then the corpus of documents labeled 1, given our word probability vector theta 1 and our document labels as well. Okay, and so we'll look at each of these pieces here, and so we'll start off and we'll look at each piece. So probability of pi given gamma pi 1 and gamma pi 0. This is equal to kind of the beta distribution with parameters gamma pi 1 and gamma pi 0, which will become, some constant. So a normalizing constant times pi raised to the gamma pi 1 minus 1 and 1 minus pi to the gamma pi 0 minus 1. And over here, so that's the first piece. I'm hoping this feels okay. And then we've got the labels coming from a Bernoulli distribution. So this is going to be a product of Bernoulli probabilities. So this is going to be the product from n equals 1 to capital N. So N is a number of documents. Okay, and so it'll be the product of pi raised to the ln, L sub n. L sub n is the label of document n, times 1 minus pi raised to the 1 minus ln. Okay, and the product then will become pi raised to the c1 times 1 minus pi raised to the c0. Okay, these are not fancy c's, these are scalar. Just c1 is the count of documents, docs in Corpus 1, and c0 is count of documents in Corpus 0. Okay, and so we have this and this, and thus these two things are of the same form, and we can just combine them. So we can probability of gamma pi 1, gamma pi 0 multiplied by the probability of the labels given pi will just become pi raised to the c1 plus gamma pi 1 minus 1 and 1 minus pi raised 1 minus pi raised to the c0 plus gamma pi 0 minus 1. I'm just multiplying this thing with this thing. Okay. So far so good? Not too bad, right? So that's the beta. Okay, and then now let's look at the probability of our word probability vector. Word probability vectors for each corpus. Okay. So theta 0, like, you know, if there, you know, will be so theta 0 is a vector of length, I don't know, on the order of 50,000, however many words we consider in our are considering, however many words to consider, and the sum of over theta 0 is going to be 1, right? So it's a probability vector, and it's the probability of each word. Okay, and then gamma theta is a vector used to define the Dirichlet distribution. Okay, and do you recall for the beta distribution, the beta distribution has two shape parameters, an A and a B, and they sort of represent like the counts of how many times you saw heads and how many times you saw tails, right? So if you saw one head and one tail, then, you know, pretty much any value of pi or your proportion as possible. So you get this flat prior. But then if you see like 5 heads and 5 tails, then that means 0.5 is more likely, okay? And if you see like 20 heads and 200 tails, then that means you know, a proportion that's quite small is more likely, or something like that. Okay. Likewise, here it's a vector used to define the Dirichlet distribution, and very similar to the way the beta distribution parameters work. This works, and so you can think of this as there. If there's 50,000 words, this will also be a vector of the same length as theta, vector of 50,000. Okay, same length as theta, and the vector will represent. Vector is like the quote-unquote counts of each word. Okay, so the first value, so theta 0, 1, okay, is going to be, this is going to be kind of like the probability. So let's say if we are, you know, our dictionary, in the dictionary, I don't know what the words are, okay? The first word in the dictionary will be A, and then maybe the next word in the dictionary will be aardvark, and then the next word in the dictionary is aardwolf, okay? Let's just say that, okay? So theta 0, 1 is the probability of the word A appearing in class 0, if that makes sense, okay? And then gamma 0, 0, 1 is kind of the, not exactly this, but it's like the count, it's like the prior count of how many, the prior count of the word A. So we're creating a prior distribution is our Dirichlet distribution, and it's defined by kind of these prior counts, right? So in the beta distribution, you had like a prior count and something like that. So it's kind of quote, quote, the prior count. And likewise, theta 0, or let's say like 1, 2, would be the probability of the word aardvark appearing in class 1. And gamma 1, 2 would be the kind of prior count of the word aardvark for class 1. Or actually, I'm sorry, we don't distinguish between gamma 0 and gamma 1. So I apologize. So gamma theta, this will just be gamma 1 is the prior count of the word A for both, and then gamma 2 would be the quote-unquote prior count of the word aardvark. And so on and so forth, you know, going from A to aardvark to aardwolf to whatever else comes next in the dictionary, to you know, all the way to the end. Last word in the dictionary being zygote or something. Zizix. Okay. So anyway, we have this, and so the probability of drawing theta, either 0 or 1, theta given our gamma vector gamma theta, this is the Dirichlet distribution. And this is going to be proportional, you know, there's a normalizing constant, but it's going to be proportional theta I goes from 1 to capital V. Capital V is number of words in the English language, or number of words in consideration. So I'll just say V is number of words in the language, and maybe we're only going to consider 50,000 words, because chances are when you do analysis, you usually throw out the stop words. So words like a, words like the, and is, these generally do not contribute towards classifying a document. So you throw those out. Okay, so I don't know, however many words there are in the language, you throw a bunch of these words out, and words that technically don't appear in the dictionary but are like proper nouns might be included in your in the thing, because they contribute to the document classification, right? So like, I don't, if you're trying to classify things on based on political categories and stuff like that, then you'd probably want to include words like Obama, which would not show up in a regular dictionary, but will definitely contribute to helping you classify a document as being politics or not. Okay. Okay, so anyway, this is proportional to theta sub I raised to the gamma theta I minus 1. Okay, so it's kind of like theta I raised to the kind of the count, its prior word count minus 1. Which is, this thing's exactly the same as the beta distribution, except in the beta distribution there's only I goes from 1 to 2, right? And the second one, by nature of the probabilities, they have to add up to 1, so it's you got theta I and 1 minus theta I. All right, so this is it's going to be proportional to this, the Dirichlet probability, or Dirichlet likelihood. Okay, and then lastly we have the probabilities of the corpus 0 given word probability vector theta 0 and the label of documents, and the probability of corpus labeled 1 given the word vector theta 1 and the labels L. Okay. The corpus, okay, so remember, we treat our documents as a bag of words. Okay, and so we have the vector Wn is the word count vector of document n. Okay, Wn is a vector of length. I'm going to just say 50,000. We're just going to pretend that there's 50,000 words of interest to us. Okay, where like W11 is the count of the word A in the first document. Okay, and W12 is the count of word aardvark in the first document, and so on and so forth. Okay, and so probably W11 will be like 50 and W12 is likely to be 0. Okay, unless we're talking about aardvark appears generally when we're talking about words that start at the beginning of the dictionary, right? What is it? Okay, and okay, so anyway, we have this. So these are our word vectors, and so the probability of the vector wn, so for document n, given its label and its the corresponding word vector. So if it's, whether it's labeled 0 or 1 will determine which word probability vector it's using, then the probability or the likelihood of that thing is going to be the probability of the word theta, theta sub I raised to the number of times that that word appears in document W. So this is, for each word I, take the probability of word I, theta sub I, and raise it to the power equal to the count of word I in document N. So if the word aardvark appeared twice in document 7, then you would take the probability of the word aardvark and you square it, because that's the probability of that word appearing. Okay? Because we're treating these words, we're treating it as a bag of words, right? It's as if we're just drawing from a multinomial, which may not be the most accurate representation of the document, but that's how we're treating this. Okay? Does that make sense there? Okay, and then a corpus then, because we're treating it as a bag of words, a corpus is then taking the bag of words, each bag of words, and then we're just dumping all the bags together in a big bucket, which we're going to call the corpus. All right, so if there's 20 documents of class 0, then we're going to take the individual bags and just dump them together into the bucket, and that will become the corpus for class 0. Okay. Yeah. So the corpus is like a bucket where we have dumped the individual document word bags. Okay, so now you just have a bucket of a bunch of words, right? And so you'll have a vector, and it's like the sum of the word counts there. Okay, and so the probability of the corpus. So we're going to call this corpus X. Either it could be where X is either 0 or 1. Okay, X is 0 or 1, okay? Given all of the labels and the theta that corresponds to X is going to just be the product for all the documents that belong in the corpus of this thing right here, from I equals 1 to V of theta I raised to the Wn I. Okay, so this is just the probability of the corpus is the probability, is the product of the word vectors, word count vectors. The probability of the corpus is the product of the product of the probabilities of the word count vectors W. Wn that for the documents belonging to the corpus. Okay, does that make sense? So we're just saying like, here's the, we calculated the probability of getting our word count vector wn, and then the corpus consists of these 10 documents, which are word vectors now, word count vectors, and we just basically take the product of all of those. Okay, so we're dealing with really tiny numbers now. Okay, and this basically, if you treat the corpus as a bucket where you've dumped all the words together, then this just boils down to I to v of theta sub I raised to the ncxi, okay? Where ncxi is the kind of total word count of word I in corpus cx, all right? So if, document 1 has the word aardvark twice, and document 2 has the word aardvark once, and document 3 has the word aardvark 0 times, okay? Within that corpus, the word aardvark shows up 3 times, and that would be our NCX for the word aardvark, okay? And so yeah, we've just dumped the words together, and we're going to kind of aggregate the counts of the individual words. Okay, so we still have a vector of length 50,000, a value for every single word in the language, but now we've dumped them together, and that's going to be the probability of our corpus. All right, is this okay? Have I lost anybody? Yes.
Wait, so like document 1 had 5 amazings, and document 2 had 2 amazings. When you combine them, you'd only have 2 amazings?
So if document 1 had the word amazing 5 times, and document 2 had the word amazing 2 times, then in the corpus, you have seen the word amazing 7 times. Okay, and so your NCX, so the number in corpus CX of the word corresponding to I, if amazing is like the 60th word in the dictionary or whatever, for that word would be, what was it, 7, okay? And you take the probability of seeing the word amazing, I don't know, it's probably on the order of like 0.001 or whatever, and you raise that to the 7th power, okay? Okay, and then, and so if we look at this probability, so this is effectively, proportional to a multinomial, and, the Dirichlet distribution is the conjugate prior, and so they combine quite nicely as well, okay? So the product of the priors, so what do we have? The product of theta 0, the theta 0 vector given gamma theta, and the product of the theta 1 vector given gamma theta, and the probability of corpus 0 given gamma theta 0, and the labels, and the probability of corpus 1 and theta 1 given, and the labels, will become the product of all of these things, which this is the product of theta. Well, basically all of these things combine quite nicely, okay? So it's going to be from I equals 1 to V of theta 0, comma I of the NC0 I plus gamma theta I minus 1, and also theta 1 comma I raised to the NC1 I plus gamma theta, gamma theta I minus 1. It looks crazy because we have all of these subscripts to keep track of. But if you think of this just as a beta and a beta distribution, like our language only had 2 words in it or something, then it's pretty much the same thing as a beta distribution, okay? And it's just the product of when you combine. Here, let me just pull up the previous slides that I'd just written. So this is the Dirichlet distribution, which is the probability of each word raised to its kind of prior word count minus 1. And then now we have the probability of each word raised to the number of times that count appears in the corpus, okay? And then so when we combine the two, it just becomes the number of times the word appears in the corpus plus its prior word count, because now we're getting kind of like a posterior probability, right? We've updated this. So if you're comfortable with how the beta distribution works, with kind of like the prior times you've seen heads and tails and the actual times you've seen heads and tails in your data, and then you just add those two together, this is the same thing, except rather than having heads and tails, you now have 50,000 words. But it's just the same idea there. Okay, is that all right? Okay, and then so the joint probability of everything so including the value pi, so the probability of the corpus and the labels and the pi and the theta vector 0 and the theta vector 1, and our prior values, gamma pi 0, or I'm sorry, hyperparameters, gamma pi 0, gamma pi 1, and gamma theta, which the article now absorbs into this vector mu. Mu now represents the hyperparameters. Okay, this becomes, and I'm just taking the values, the thing that we had earlier, pi raised to the count of document 1, gamma pi 1 minus 1, and 1 minus pi, the count of documents in class 0, plus gamma pi 0 minus 1, and multiplied by this thing right here, which we just did. Shrink that in there. Okay, and we do that. So we just have this, okay, and this is equation 33 in the literature, in the article. Okay, in section 2.4.3, we are going to integrate out the value pi, okay? And in the interest of time, we integrate out the value of pi. Okay, and this is to help make our calculations easier. And what we mean by that is we are going to integrate out the value of pi just so that pi doesn't appear in the result. And this will just, we consider all possible values of pi, okay? So we would say, is the probability, because we're saying the document itself is a random draw, like and depending on pi, it might be likely to be class 0 or likely to be class 1. So if pi is 0.99, then most of the time it's going to be class 1, and only 1% of the time will it be class 0. And on the other hand, if pi is a lot smaller, then it will be class 1 very, very rarely and class 0 quite frequently. Okay. And in section 243, they do some math to integrate out pi. The result looks crazy, okay? But the result basically turns this part over here, after integrating out pi, this part becomes just a crazy, kind of a crazy constant, okay? Well, not a crazy constant, but this becomes, scary looking formula that does not depend on pi. Okay, it just depends on the counts, the prior document counts and the actual counts of the corpus. Okay. So now we only have this part to worry about. So after integrating out pi, this part we successfully get rid of the pi's, and we get kind of this crazy looking formula that does not depend on pi, but just kind of the prior counts. Okay, so the Gibbs sampler now. Oh dear, I'm gonna run out of time. The Gibbs sampler will sample our parameter values one at a time, kind of using all other values setting all other values fixed, or I should say conditioning on all other values. Okay, so and let's think of the number of parameters we have. We have LJ, so we've got J documents, and each document has a label. Okay, so we need to sample J parameters here. Okay, and this label is probably what is of interest to us. Okay, and then let's do and then we've got to figure out theta 0 and theta 1. Okay, so we've got to these come from the Dirichlet distributions. Okay, and we need to sample these. So we have basically J plus 2 parameters to sample. Okay. And so we're gonna try to sample sample the label, okay, so we want the label LJ, okay, and so when we sample this, there's only two possible labels, 0 or 1, so we're sampling basically from a Bernoulli distribution. Okay, we want the label LJ, which is sampled from basically a Bernoulli distribution, okay? And this is given the vector. So this is the vector of labels without document J. Okay, because when we're trying to sample the value we have for document J, we can't include document J into the corpus, and we can't include it into our labels. So we have this notation to say this is all of the other labels. So if you got 50 documents, this is a vector of 49. Okay, and then you've got the corpus that does not include the words that belong to document J. So this is kind of the corpus that does not include document J. Because the words in document J are kind of unclassified right now. And then you still have the theta 0 vector, the theta 1 vector, plus your hyperparameters. Okay, this boils down to, and I'm going to kind of skip ahead in the thing. We've got, so x could either be 0 or 1, okay? It's going to be the count okay, so this is kind of like the proportion. Kind of, this is technically like the mean of the posterior of the beta distribution, right? So if you recall the beta distribution, the mean of the posterior is kind of like the number of tails observed, or number of heads observed, plus the prior head count minus 1 divided by the total number of flips in the document, or number of flips in the data set, plus kind of the prior values minus 1. And let me just kind of show you like conjugate prior. Oh, maybe I shouldn't be doing this because we're going to run out of time. Okay, so yeah, you have A plus kind of the number of successes, and A, and then your posterior predictive is going to be basically this, right? So that's kind of what we have here, and then you multiply that by the probability, the likelihood of the words in the document. Okay. Okay, so this is kind of the mean of the posterior beta. Okay, I know I'm running out of time, but I kind of just want to do a small illustrative example. Yeah, Carl.
For the count, is that including document J that we're talking about for the document J is currently in? Or is the minus one taking care of that?
So this doesn't the J doesn't play a factor into here. This is total number of documents and I think so. You're asking me on the spot, Nate. I'm not 100% confident right now at this moment. Okay, let me. All right. Let's say there are. I know I'm running out of time. Okay, but let's say there are only 4 words in our vocabulary. Okay, we got apple, banana, cat, and dog. Okay, and let's say we've got four documents. Okay, and document 1 is 5601. These are the counts. Documents 2 is 0, 2, 8, and 7. And document 3 is 4, 2, 1, and 1. And document 4, let's throw in a 5th document. Okay, we got 6, 3, 0, 0, and 1, 2, 9, and 10. Okay, so our corpus altogether is going to be the total number of words that we have. So we've got 10 and 16 and 6, 12, 15 and 18 and 19. Okay, and then currently, so we'll start off with a random sample of L. Okay. And so let's just randomly sample, and let's say these were labeled 1s and these were labeled 0s. Okay, like when we look at this, we can obviously tell, I think, that document 4 and document 1 are of the same class, and document 2 and documents 2, 3, and 5 are of the same class, right? Like documents 1 and 4, documents, 1 and 4 are about fruits. Oh, and document 3. 1, 3, and 4 are probably about fruits, and then documents 2 and 5 are about, so the truth is probably documents 2 and 5 are of class 1, and documents 1, 3, and 4 are of class 0, okay? But let's say this is what we have, then if this is our current thing, then our corpus 0 is going to be the sum of kind of these things. We're going to have 9 and 10 and 9 and 9. This is not great. And then corpus 0 or corpus 1, those word counts will be everything else. 7, 5, 9, and 10. Okay, this is right now there's not much distinction here, okay? But when we want to do document 1, so we'll do doc 1, and we want the label L1. This is going to be coming from, so right now we have a total of 3 in corpus 0 and a total, I'm sorry, I have this all labeled. I'm sorry, I did this part wrong here. This should be 0 and 1s. 0, 0, 0, 1, 1. 0, 0, 0, 1, 1. We have 3 in corpus 0 and 2 in corpus 1. So L1, the probability here is going to be equal to Cx plus gamma pi x minus 1 and n plus gamma pi 1 plus gamma pi 0 minus 1. So this part will become 3 plus, I don't know what our gamma priors were. Let's just say we had 2 and 2. So it would be 3 plus 2 minus 1, and then over here we have 5 documents plus 4, 2 plus 2 minus 1. Okay, and so this is kind of like our posterior mean for the classification. multiplied by the word probability vectors, okay? And so the word probability vector is going to be theta xi raised to the thing, and so we need to have kind of a theta vector, and we'll say if it's a word of a document about fruit, maybe it's going to, you've got high probability of using the word banana, high probability of using the word apples and bananas, and then we got 0.05 and 0.05. Whereas if it's going to be a document about animals, you know, we might have 0.1, 0.1, and 0.4, and 0.4. Then we would multiply this by our word probability counts. So for document 1, we would take 0.5, raise it to the 5th power, times 0.4 raised to the 6th power, times 0.05 raised to the 0, times 0.05 raised to the 1. Versus if we say, what is the probability of it being the other kind of document, then it would be 0.1 raised to the 5th, 0.4 raised, and 0.1 raised to the 6th, 0.4 to the 0, and 0.4 to the 1. And we would have different probabilities there, and the posterior probability of considering all of this will say, based on this vector, it's going to be document 0. Okay, because document 0 aligns a lot closer to the values of the words that we see, the counts of the words that we've seen in our thing. Okay. Your homework 6 is to code up the algorithm in R, and there is pseudocode on page 17 that I think will be very helpful in your coding it up. And I hope this is a fun exercise. So anyway, that's it. Good luck as you guys study, and we'll see you guys on Friday.